So the way that I'd like to do these, at least this week, is spend a bit of time carrying on with the story, because we're quite close to the end of the story. We've done all the physics now to the application to explain about degeneracy. But after this, if I send you a pat paper every Monday and, I don't know, send you the marking scheme on Friday or something, give you a chance to do it, unless you want it earlier, but you can let me know that. Or I just send them both to you. I suppose it doesn't really matter, but don't look at the marking scheme till you've tried the paper, because that's the way you get the best out of it. And then next week, the first bit of the session, it can be, do we have any questions? Or what would be easier, to be truthful, is because I had a word with my son about maths, and he's quite happy to organise a session to discuss any issues that come up with maths. And the reason that he's slightly better placed for it than me is, one, he went to Oxford, so that's kind of nice, because you might have questions about the concept of Oxbridge, which you can ask him. That would be quite useful for you. But two, he did all 3 A levels in maths. He did 6 A levels, and 3 of them were maths, further maths, and additional further maths, which don't exist anymore. Before you ask, Paul. So when things like mathematicians talk about proof, that kind of thing, he's in a far stronger position to talk about the way that these things work for mathematicians than I am. So I look at maths from the perspective of a physicist. He's got a degree in physics, but he's also got a second degree in maths. So he's probably in a stronger position to give you good quality information. So the easiest thing might be, if every Monday I send you a pat paper and the marking scheme, don't look at the marking scheme until you've had a chance to try the pat paper. You can, if you want to try and get the best out of it, try it on your own first with no help, and then try and use some help. If you can't remember certain equations, or I think you are. I need to check that. My memory is that the latest version of PAT, which changed I think 2 years ago, you are allowed a calculator, although originally you weren't. So the ones that I'll be sending you, the maths part was not meant to be with a calculator. So when you see a maths question, have a think about it with respect to, how would I do this without a calculator? And if you don't know how to do it, that's okay, then use a calculator. But maybe, if you go for your second attempt with some help, maybe change color just so that you know which bits you did from your head and which bits you did with help. And then during the week, if you can let me know just questions like, I didn't really get question 4, or I've looked at it and I don't really understand question 4, or I didn't, etc. If you do that, it means that Christopher and I can have a look at them, and we can decide, I'll take some of them and he'll take some of them, that sort of thing. So we can try and help you in the best possible way. We've looked at what I referred to as the quantum energy equation for kinetic energy. And it's called a quantum equation because it has what's called a quantum number in it. Now, what's a quantum number? A quantum number is a parameter, a quantity in an equation that can only take integer values and is determining the system in some way. It's a variable, again, an integer variable that determines an important part of the system, in this particular case, what the kinetic energy is. Quantum equations do not tend to be continuous because of this discrete nature to the quantum numbers. They can only take integer values. So now that I've got a free page, and what we did was we basically looked at the quantum energy equation for the kinetic energy of a free particle. Now, I chose to do a free particle because a free particle has the advantage of not having any potential energies. And potential energies, if I want to talk about the energy of a particle, whoa, that was weird. If I want to talk about the energy of a particle, I have to talk about the kinetic and the potential energy And that's suddenly now more complicated. I prefer to try and keep things simple if I could, which is why I'm going for a free particle. And the word free here means that there are no potential energies. So it just keeps the total energy nice and simple. I don't really have to worry about a conversion for a kinetic to potential. I don't have to worry about potential energies because potential energies tend to be more complicated. The equations are more complicated. So that's why I went for a free particle to get rid of the potential energies. And the danger is that people think that a free particle is like something that you can imagine but doesn't really exist. But we have three important examples. So let me just start making some notes here. So this is basically our discussion of degeneracy and why it is important. Okay, so we consider a free particle, i.e. no potential energies. The particle is confined. That means exactly as we've kind of discussed before, and how you would imagine the word confined actually is kind of used in English. So when I say that, what I mean is that a particle is held within a given space. Normally, like in 3D, that would be a volume. It's confined within a given space by confining walls or barriers. If we wanted to draw it potential energy wise, consider the potential energy of such a system, then it would look like this. In other words, the potential energy is zero within a certain space, but when you reach the walls, the particle cannot, I don't know why I wrote walls there, the particle cannot get over them. It cannot go somewhere else. I think we had a conversation briefly about quantum tunneling recently, but I'm assuming that there is nowhere else for them to go, so quantum tunneling won't work. And basically it means the particle hits a barrier that it cannot get over, an energy barrier. The potential well. And I think it's the idea that it's a bit like a water well. You know, you drill a hole in the ground from which you can get water. And if you were stuck in the bottom of the well, you're in like a gravitational potential well. You can't get out because the walls. There's no concept in this particular situation of like climbing up the walls. Right. Okay. So that's the kind of situation we're talking about, and the examples, and they are important. Important examples include, okay, free electrons in a metal, particles in an ideal gas, and particles in the sun. And those are kind of like the big three that all have kind of, you know, important things that we could talk about. Free electrons in a metal is quite an important one because we muck about with metals a lot. You know, we talk about them in electrical circuits and that kind of thing. We talk about the properties of them. We talk about what happens when you know, electrons move through a metal and it generates a magnetic field and all this kind of stuff. So free electrons in a metal are quite important. Everything to do with conduction and magnetism basically is coming from them. It's quite a big area. Particles in an ideal gas, okay, we do that when we do thermal physics. It's kind of like a third of thermal physics. if you remember, thermal physics is basically some basic ideas about thermal physics, about energy, things like work, heat, internal energy, what temperature means, those kind of things, the Maxwell-Boltzmann distribution. The second part of thermal physics is about states and phases. This is where we learn about how the atomic arrangement in a material can change or be modified based on the temperature, and we link the temperature to putting in or taking out energy. And that's where we got vaporization, delta E equals ml, and just a change of temperature, that's delta E equals mc delta T. So this is where we talk about change of phase and change of state. That was the second bit of thermal physics. And the third bit of thermal physics is ideal gases. So ideal gases, I'm not saying they're not important. They are kind of important, but they're a third of thermal physics. And thermal physics is not a massively large topic area for us, so it's probably less important. Now you might say, well, particles in the sun is not very important because we haven't even done any astrophysics yet, but we are going to do astrophysics on both the IB and the A level. There is a big chunk of astrophysics, and I think that you will find when you do it, it is quite large and it is quite important. And the really nice thing about the application of this business of degeneracy to particles in the sun is it allows us to understand how stars die, and that allows us to understand in part some of the nature of the universe. So that's quite important. Anyway, so and the first one I think we were talking about was, as Christine comments, free electrons in a metal. Now when we consider free electrons in a metal, let's just do that. And again, I'm still sort of summarizing, I think, what we've done so far. Free electrons in a metal. We've discussed the idea that if you have a solid, and if you have obviously the solid is made up of lots and lots of atoms. If you have a description of the atomic arrangement, you end up with positive nucleus, and you end up with, in this particular case, I'm going to draw 3 because I'll be here all day. You end up with a positive nucleus, and you end up with a bunch of orbitals. And one of the nice ways of thinking about this, how this arises, is to imagine that we made up this 3-particle, tiny little, I'm not sure whether I'd really call it a metal in that sense, but 3 atoms. And it's got electrons in it. Let's zoom in on the picture here. And let's shove some electrons in. Now the inner orbital can take 2. And we said that all the orbitals can only take 2 electrons. That's quite important. And when the chemists in the past have said that you can have 2 electrons in the inner orbital, and then you can have 8 electrons in the next orbital, this is not true. As we said before, a more correct description is that there just are a bunch of orbitals, and some of them are very, very, very close together in energy, and they're lumped together. So there is only 1 orbital there, and you can get a maximum of 2 electrons in an orbital. This one here, it's actually 4 orbitals, and you can get 2 in each, which is why it's 8. So when chemists talk about the fact that the second orbital can take 8 electrons, this is not true. There's actually 4 orbitals there, and each of those orbitals is quite close in energy to the others, and each one of them can take, again, 2 electrons. So yeah, that's the kind of way it works. And there's a system of naming these orbitals, which I mentioned last time. It gets quite complicated. This is this business of, that would be 1s, the 1s orbital, which can take a maximum of 2 electrons. This is now the second what the chemists normally refer to as the second orbital, but actually it's 2s, and you add another type, 2p. And each time you go to the next sort of orbital, you call it the next number up. So this would be 3, and it repeats what you had before, so a 3s and a 3p, but it adds a new one, 3d, and then you go to the next one, that would be 4. So 4s, 4p, 4d, and you add a new one, 4f. And this is the kind of way it works. And there's one s orbital. One. Then I've got p, then I've got d, then I've got f, and they go up in odd numbers. There are 3 p orbitals. We don't need to worry about how they name them. They actually call them px, py, and pz, but that's not important. There are 5 d orbitals, which of course each orbital can take 2 electrons. So there are so-called 10 d electrons if it's full, and then 7, so you can get 14 f electrons. These are the lanthanides. The first time that comes up is at the bottom of the periodic table, and it's called the lanthanides because lanthanum is the first one. The next one down in the next row are called the actinides, because the first one is actinium. Yeah, and the for your information from kind of GCSE, or maybe, as Christine knows, I have slight issues about talking about MYP just because I don't know what you will have been taught. But the first time the d orbitals come in, as you can see, is number 3. So the first d orbitals are 3d, and they are called the transition metals, which include iron. So yeah, so this is the way it works. So I've got 1 s, and I've got 3p, and I've got 5d. So if you look at that, that's 5, 6, 7, 8, 9, 2 in each one, so I can get 18 in there. And that's where all this lot comes from. So as you can imagine, don't get too upset about this. As you can imagine, things are slightly more complicated than you've been told before. Don't get upset by that. That's the educational process. Basically, before you learn like mega amounts of detail and complexity, you have to try and grasp the simpler structure first. So, and I think what we did was we said, let me put another 2 in here on the basis that I'm drawing individual orbitals. So another 2 there, and another 2 there. So this is, you might consider that this is, so far, that's the 4th one in the periodic table. And then I'm going to put 1 more. Now there would be, I'm going to say there's 1 more in the next orbital. So there, there, and there. If those orbitals were still the circular orbitals that we normally draw, just overlapping is the way that I should have done it, then that would be the extra orbital. So that would be 5. So what is that? That's hydrogen, helium, lithium, beryllium, boron, or is it boron, beryllium? Always get that the other way around. So I think this is beryllium, although, yeah, I think it's beryllium. Number 5 in the periodic table. But I don't really want to draw them like that. I've sort of drawn them like they're stuck around the nucleus. But because this orbital has merged together, they could be anywhere on it. Like that. And it makes it look like, because I've got 3 atoms, and I've actually got 3 electrons, 1 for each. So we're basically drawing total number of electrons per atom is 5. Now I've got 3, so that means there's a total of 15 electrons in this system. These things are called core orbitals. And these are called hybridized orbitals. And these are called core electrons. And there are no prizes for guessing that these are called hybridized electrons. Now, electrons are electrons. So when we call them core, or we call them hybridized, it doesn't mean that they've changed in any way. It is a reference to the kind of orbital that they are in. The core orbitals stay around a nucleus, like they do with an individual atom. The hybridized orbitals contain hybridized electrons, and that just means those electrons are free to move around because the orbital that they're in extends everywhere. So this is what we sometimes call the free electrons, because they are free to wander all around the material. They're not free to leave, but they're free to wander around. So I think, first of all, we need to get in our head that the description of a metal is normally given to students as metals contain free electrons. Non-metals do not contain free electrons. This is not quite true. The situation is that for all materials, for all solids, there are core electrons, which are not free, and all materials have free electrons. Glass, which is an insulator, an electrical insulator, and a thermal insulator, heat does not travel well through glass. It doesn't, we say, okay, it's an insulator because it doesn't have free electrons. That's not true. It does have free electrons because its atoms have to come close enough so that they start to then repel. So there must be overlap of clouds. So it does contain free electrons. So the things that you've been told in the past, which is basically the thermal and the electrical properties of sort of conductors, is based on the fact that there are free electrons. And the insulating properties of the non-conductors is because they don't have free electrons. This is actually a lie. You've been lied to. They all have free electrons. So clearly, we said that to you, and chemists said that to you, because it was just a simple way of trying to get over the idea that, you know, there are conductors and there are insulators, and we need a decent example to explain why. And it just seemed like, you know, free electrons was the easy way of explaining it. But it's actually not true. So there must be a deeper understanding here, which is kind of where we're going with this. Now, before we do that, let's just look at this hybridized level, because the hybridized level, if we were to zoom in on it, well, if it was a single orbital, if the three orbitals, the 3/3 orbital, just became one, which is kind of the way that I've drawn it there, then I've now got a situation where I've got one orbital, but I've got 3 electrons in it. Well, you can't get 3 electrons in an orbital. I think the very last thing I ever said to you last time we got together was this situation of only having 2 electrons in an orbital and no more possible. That creates 3 options for any orbital. 1, it's got no electrons in it, which means it's empty. 2, it's got 2 electrons in it, which means it's completely filled. And 3, it's got 1 electron in it. It's either 0, 1, or 2, because it can't have less than 0 and it can't have more than 2. If it's got 1 electron in it, it's half filled. Now, in this situation here, it would appear that if those 3 orbitals got together and just became 1 orbital, then I've now filled it and another half. And that's a bit weird because it's sort of not allowed. When we look at it really closely, what it turns out to show is that there are actually the 3 orbitals or shells from each of those atoms still exist. They're just stunningly close together. the 3 orbitals are still there. Now, if you think about what this means for the electrons and this business of being like no filling, empty, half filled or full filled, this sort of makes sense because intuitively, if you think about this electron here, when it was in the orbital that is that orbital, it half filled the orbital because there was 1 in it. And that orbital was half filled, and that orbital was half filled. If these atoms were not together, forming this hybridized level, but actually they were apart, then that orbital will be half filled. Well, now it's become an apparent like single orbital, but now it turns out it's not. It's actually 3 very close together in energy. And each of these 3, by the way, is not associated with a particular atom. So we don't say like, you know, the middle one is that one, and that one is like the one on the left, and that one's the one on the right. We don't say that. We don't really associate these 3 orbitals with individual atoms. We just say that there are 3 orbitals there. The structure, when it hybridizes, has made this kind of like triple orbital. And because there's 3 electrons in it, 1 from each of the atoms, then it will be half filled because those 3 electrons will be in here. And because there's 3 orbitals, each one can take 2 electrons. That means a maximum of 6. And there's 3, so it's half filled. So when I say that there are 3 electrons in this outer hybridized orbital, that's half filled because it can take a maximum of 6, because there are actually 3 there. So this is still half filled, which is good because it, again, intuitively, it makes sense. The orbital has not changed its nature when you put atoms together. It was half filled, it's still half filled. It's changed its nature in the sense of where it's kind of located, because now it's extending over the whole material. But with respect to numbers of electrons and this golden rule, if you like, that you can only get a maximum of 2 electrons in an orbital, it still works. If I had a mole of material, if you remember Avogadro's number 6.02, let's just call it 6, just for simplicity, 6 times 10 to the 23 atoms. So let's say we got a mole of iron. There'll be 6 times 10 to the 23 iron atoms there. Okay, well, that means that in a hybridized level, if it was filled, then the hybridized level, when I looked at it in really close detail, there would be 6 times 10 to the 23 orbitals there, 1 for each of the atom. Each atom brings its own orbital to the party. And if it was filled, if that orbital was filled in the actual atom, then in the solid, it will also be filled, which means that if it was filled around an atom, it would have had 2 electrons in it. In my mole, it would have 12 times 10 to the 23 electrons in it because it's filled. Now, there are other orbitals. If I go back to my diagram, there are other orbitals here. Now, I'm only considering total number of electrons per atom is 5, but the other orbitals still exist. They just got no electrons in them. When chemists and physicists talk about electrons being promoted or excited and jumping up to higher orbitals, we call that excitation. And then they fall back down again because they want to be close to the nucleus because of the attraction. We call that relaxation. They're going into the orbitals that at the moment are empty. So these orbitals still exist. There are other orbitals which by definition are going to be hybridized, because the hybridization is caused by the overlap. So if the outer orbitals, which don't have any electrons in it, if they're overlapping, which they obviously are, if this orbital is overlapping, then ones further out definitely are, then they're all hybridized as well. I don't want to destroy my text there, so let me just go around like this. And there you go, there's another one, and there'll be another and another and another and another. And right, okay. So we've got that situation. Let me go back here. Okay. As we add more and more atoms to the system, each hybridized orbital has another orbital as part of it. Let's just make sure we understand what we mean by that. So if I had 3 atoms, then that first hybridized orbital has got 3 orbitals. When I add another one, so now I've got 4 atoms, that first hybridized orbital, which will now extend around all 4, that's got 4 orbitals in it. If I had 6 times 10 to the 23, it's going to have 6 times 10 to the 23 orbitals. Every atom that you add to make up a bigger and bigger lump of stuff adds another orbital to each of the hybridized orbitals. Okay, the energy level diagram. Now, physicists try to explain about what electrons can do around a nucleus, particularly with respect to relaxation and excitation, by using an energy level diagram. If we have a single atom and imagine an electron excited from one orbital to another. Then basically we have this sort of situation. If I just draw that and I put an electron here and I say that it rises up and it's going to end up being there, that's what's going to happen. That's called excitation. To explain this as simply as possible, we draw an energy level diagram. And basically it looks like this. You can now, I'm going to make this look simple just to get over the idea. Imagine that's the first orbital. Imagine that's the second orbital. Imagine that's the third orbital. I'm going to draw 4. There's the 4th orbital. There's my plus at the center. What we do is we imagine that there's an energy associated with that, and an energy associated with that, and an energy. Now, I'm kind of indicating on here position, because it's like, distance from that line. And that's not really what I'm trying to do. All I'm trying to show you, that didn't work very well, sorry. All I'm trying to show you is that the y-axis here is potential energy, and there is a line for the energy these are called energy levels for the orbitals. And that's what an energy level diagram is. In reality, the delta E is not constant. So I have shown a delta E there and a delta E there and a delta E there, and it looks like they're all the same distance apart, and that's because when you draw orbitals you just tend to draw them equally spaced. But in reality the energy values are not proportional to the physical size of the orbital. That's the first thing. And the second thing is the orbitals aren't necessarily equally spaced. So so what tends to happen is as you go to higher and higher energies, the orbitals get closer together. In reality, the delta E is not constant. E.g., for hydrogen, it looks like this. Now, this is potential energy. The x-axis doesn't mean anything. It's just energy values on an energy line. So if you put one there and then just put it quite close and then move it further apart. Can I get rid of that bottom one? Yeah. And then move it further apart again. And then further apart again. So you can see it looks like as you go to higher and higher energies, they get closer and closer together. That tends to be what happens. As an example. Okay, so what does this look like? What does an energy level diagram look like for hybridized levels? So in other words, where you haven't got a single orbital with a single energy level, you've got a pile of orbitals, all with slightly different energy levels, energy values. Then what you'd do is you'd have to take this kind of idea. Now, go on to the next page. So basically, if we have the atom compared to a solid, then for the atom, we have an energy level diagram that, okay, I messed that up, sorry, because my tablet moved while I drew that. Okay, so I've got an energy level diagram that looks like this. I'm just going to repeat this again. So we've got one there, quite close, a little bit further apart. Let's just do it like that. Okay. So what happens? Now remember, the inner orbitals are core. So I'm just going to assume that these two are core and these two are hybridized. Okay, for a solid, the core electrons stay the same because they are single orbitals with single energies. So there's no difference there. It's the hybridized ones. Now the hybridized ones, can I just make them two different colors? Actually, can I just adjust my diagram and just have one hybridized? Because my diagram, you'll see why in a moment. Now, the way that I've drawn this, these energy levels are the same. And of course, this one should be there. But because it's hybridized, it's not a single energy level at a single energy value. There is one of those for every single atom that's part of the structure. And what happens is I'm not drawing them wide enough, am I? If I just kind of like have them sized up the same length. That would be if it was core, but because it's not core, I have lots and lots. If I have a mole, then I've got to try and get 6 times 10 to the 23 horizontal lines here with ever so slightly different energy levels, ever so slightly different energy values. And that's what happens. And we actually call these levels, and we call this a band, an energy band. It's a ridiculous number of energy levels very, very close together, and because they're not allowed to have exactly the same energy, because that would mean that then I'm going to end up with problems having electrons, too many electrons per energy level. If I keep that, again, as almost my golden rule, I am stuck here. I have to have my ridiculous number of energy levels in the hybridized orbital ever so slightly close together, but not exactly the same. And yeah, I end up with bands. So for a solid, the energy level, and I'll use the word carefully now because I'm going to use the word band as well. The energy level diagram always has, okay, can I, okay, always has core levels plus hybridized, oh gosh, I didn't want to use that word, sorry. Always has core levels plus bands. Now, if you think about this, there's 2 elements where that's not necessarily true. Hydrogen and helium. For hydrogen, there is one orbital because there's one the inner orbital is the only one that we're thinking about here. It's half filled. It's got 1 electron in it. If I make solid hydrogen, which is really difficult to do, but because you have to be incredibly cold. But if you make solid hydrogen, then you end up with hybridized levels, and you've only got 1 with electrons in it, which means that you don't have any core levels, and the same for helium. So this is not true. For hydrogen and helium, we only have a band, or bands. And it turns out that the electrical properties of a solid are purely determined by the situation at the top of the energy diagram. And you only have a couple of options. Now at the top, I don't know why my dogs are going mad. At the top, it's always hybridized levels. It's always bands. If you think about it, it has to be, because the orbitals overlap. Oh, someone at my door. 1 second. Amazon delivery. Amazon delivery. Ooh, this could be like people. I'm not quite sure how boring this can possibly be, but people on YouTube actually do openings. Like people are interested in. So let me do an opening for you. I'm going to open this. Okay, the kind of thing, the tab that you pull is broken. That's not very good. It's got a warning on it about emergencies. Oh God Almighty. Okay, it's got here, for emergencies call this number, and it actually says global response access code. Global response. I could call this number and I could say, okay, 333146 emergency, and there'd be a global response to this. Wow, what on earth could require a global response? It's actually, Christine, you know, we were talking about cycling earlier. I don't know whether you're talking, but you're muted.
Oh yeah, sorry. Yeah.
It's a light. It's a set of lights for my bike, and they're from. I think they're from. They look like they're from China. They weren't meant to be from China, but they look like they are. All steps to redeem the gift card. I've got a £10 Amazon gift card. Wow, that's interesting. That's really interesting because this only cost me £3.99. That's like a win for me. I don't understand that. And here you go. My rear light is really tiny. Ooh. But the front light is quite big. And when it's charged up, it clips on with a bit of kind of silicone thing. So you just shove it on the bike and wrap this around the handlebars, clip it on. So it's on and off in seconds. When it's charged, you can fit a sensor to the wheel. So it becomes a light, which is light sensitive. So it's not very bright when it's light. And as it gets darker, it increases its intensity, which is quite interesting. And also, it shows you your speed on the screen. That's quite cool for £3.99. That's ridiculous. Right, okay. And so I will shove those on charge later and see how good they are. But I'll move on. And right, okay, so I've kind of forgotten. Let me kick back in gear here. So it turns out that the electrical properties of a solid are purely determined by the situation at the top of the energy diagram. Okay, and as I said, if you think about this, that's energy bands. When the atoms come together and then they stop because there's a repulsion that stops them, like, you know, coalescing into one, that's because of electrons overlapping and getting too close together. So the outer electron orbitals with electrons in, it's always going to be hybridized. So basically, we're not interested in the core orbitals at all. The properties, the electrical properties of a material are nothing to do with the core electrons and the core energy levels. They are all to do with the energy bands. And it might be, for example, that the overlap does not just include the very, very outer shell. It may be that because the nuclei, imagine you have something like iron, for example. Now, iron has got 26 protons. The attraction, if you like, between the nuclei is actually quite large because it's 26 plus. And sorry, I'm being stupid when I say that. Because it's a repulsion between the nuclei. Sorry. When you have something like iron or aluminium, something like that, the attraction is sufficiently strong that as the first orbitals start to overlap, they could overlap quite a bit. And if you remember, I said, as you go to higher and higher energy levels, they get closer and closer and closer together, which means when the one starts to overlap, and then eventually stops, the repulsion stops it, if the next one in, if the one that we might have called the core orbital, if that one is sufficiently close in energy to the outer one, then it will become hybridized as well. So it isn't just that there's only one outer hybridized level that kind of exists with electrons in it. There might be two, maybe even three, depending on how close they are together. Not relevant. We're only interested in the outer one, and there's only two situations here. Pretty different from the situation at the top of the energy level diagram, and there are only two options. And the two options are this. We either have I'm just going to draw it like that. One level like that. Sorry, one band like that, and one band like that. Or, now bear with me, because it looks like I'm just going to copy and just paste something that's identical. Because literally the way I'm doing it, it is. So option number one is where I have a hybridized level and it's got some electrons in it, and it's filled with electrons. And that one's empty. Now that would be a situation where, a bit like helium, the outer orbital that becomes hybridized has got two electrons in it, so it's filled. And the next one up didn't have any in it. So that's hybridized, but it's got no electrons in it. So that's the situation there. And the only other one is one. Now, I said there are three options here. There's either no electrons in the orbital, there's one electron in the orbital, which means it's half filled, or there's two electrons, which means it's completely filled. Well, this situation here is the situation that shows no electrons in it, it's still empty, and two electrons in it. If I was to draw the next hybridized level up here, if I was to do another one up here like this, that one would be empty as well, because that's another one of the outer orbitals that had no electrons in it. Okay, the only other option is where the level was half filled. And that is normally drawn like this. I'm just shading it because there's like, there's like 10 to the 26 electrons in there if I had a mole. That's half filled. So basically this situation of I can only have no electrons, one electron or two electrons, empty, half filled or filled, gives me two situations for the top of the energy level structure. I either have a filled band and then a gap and then the next empty band, or at the top I have a half filled. And actually this bit here is just not relevant. I'm only interested in that. The only bit we're interested in is what the situation is at the top. Is it a filled band with a gap and then an empty, or is it half filled, which means I've got filled next to empty, next to unfilled, kind of here. Okay, so why does this determine the electrical properties? So consider, we're almost at the end of this now, guys. Consider what happens to electrons when an electric field or a voltage is applied. Okay, so the process is you apply the voltage. That would be like saying you turn the battery on, you close the switch. An electric field is set up in the circuit. The electrons feel an electric force. The electrons accelerate. The electron energy rises. Now we have formulas for this, of course. Now I apply a voltage, I'll just call that V. An electric field is set up in the circuit. Now the equation for an electric field depends on the situation. So I'm just going to use the symbol for electric field, which is capital E. If it was two plates, for example, and we applied a voltage across there, then and the plates were a distance d apart, then the electric field strength between the plates would be V over d. If it was a charged object that was isolated, like imagine you've got like a little sphere that's hanging from an insulating thread and you've charged it, then it has an electric field that looks like this. The electric field there looks like this. The electric field here looks like it's radial. It goes outwards along radii. Then the electric field there is given by some constant times the charge divided by something called 4 pi epsilon. I don't think I want to write k because I'm mixing up my constants here. Forgive me. It's q over 4 pi epsilon, and it's going to be r. Where's my pen gone? R squared, where r is the distance from the center. So it depends on the situation. In an electric field in a circuit, that's quite complicated because it's going around a weird shape and through different material. So that's quite complicated. So, but the symbol that we use for electric field strength is capital E. Now, I should say to you that you've done about gravitational field strength. Gravitational field strength, which is sometimes written as little g, 9.81. It's the acceleration due to gravity, but it's also the gravitational field strength. That is the force per unit mass. That's the definition of gravitational field strength. If you look at that, rearrange it. F equals mg. That's the weight. Weight equals mg. Mass times by gravitational field strength. Rearrange that there. Rearrange it for F. F is mg. F is the force due to gravity, which we call weight, and that's why we give it the symbol W. So gravitational field strength is force per unit mass. Electric field strength is force per unit charge. So, and you'll do that. I don't know whether you've done that yet, Christine, with Mrs. Edwards. But go on, Christine, you're going to say something.
We've done that with Miss Edwards.
Okay. Paul, you won't have done it yet, I think, because all of the electricity at A level is left until the 7th form.
Yeah, I haven't done it yet. Okay.
How's your hand, by the way?
It's coming out of the cast in 8 days.
In 8 days' time. Okay. That'll be nice. The electrons feel electric force. Okay, well, that's just going to be, so E is F over Q is the electric. So just rearrange it. F is EQ or QE. That's how you work out the force on a charged object in an electric field. It accelerates. That's F equals MA. And the electron's energy rises. Well, if it accelerates and goes faster, then obviously its energy increases. So you have to ask yourself, did I ask On the previous page. Consider what happens to electrons when an electric field is applied. Okay, so when you apply an electric field to a circuit and you look at what happens to the electrons, it's this process here. Now, on an energy level diagram, the x-axis doesn't mean anything. It's just a number line. That's all it is, with energy on it. So, as the energy of the electrons rises, they move upwards on an energy level diagram. Now, sorry, I didn't want to do that. If we got this situation, here, then if I just look at one electron here, it wants to move upwards, but it can't. Can't move up because there are no levels above it. The amount of energy that is given to an electron as a result of an electric field is kind of like a dot on there. It's kind of like it's that little bit there. It's a tiny amount of energy, and the electron can't do that because it's in a filled band. There's a gap between its energy that it can have and the next possible option for an energy. It would be like trying to say, I'm going to get an electron in an atom to not jump up to the next orbital, but to jump up like a tiny little bit of the level. It can't do that because it'll drop straight back down again. It doesn't work. It can't make use of that energy. So for filled bands, the phrase that uses filled bands do not conduct electricity, because they can't, because you have to allow the electrons to move upwards, to be excited. Now here, an electron can easily move up. That's supposed to be a tick. So the electron is next to unfilled levels and can easily have its energy higher. So the conclusion we come to is filled bands cannot conduct electricity. Half filled, because remember that's the only other option. Okay, why is my pen stopped? Half filled bands can conduct electricity. So how has this sort of changed our view now? In a metal is a metal because its upper level is half filled. Something that's not a metal, not a conductor, is something that has an upper level, a band, that's become a band, and it's filled. And the question is, just as my final note here, note the size of the gap in energy determines if a material is a semiconductor or an insulator. And the way that we draw it is we normally draw it like this, rather than keep doing this, which is a pain and never looks beautiful. We normally draw it like this. Okay, if that energy gap, EG, is approximately like 2.5 electron volts or less, that's what we call a semiconductor. If this is greater than about 5 electron volts, that's what we call an insulator. I shouldn't have said approximately. Less than or approximately equal to. And then there's a bit in the middle where, you know, between 2.5 and 5, where it sort of depends. It depends who you are and what your research is as to whether you say that you're actually doing research on insulators or semiconductors. Basically, your electrons are here. And the size of that gap determines whether we call them semiconductors or insulators. A semiconductor is the gap is sufficiently low that although electrically you can't provide the energy to get the electrons to sort of make the leap across like that, which is what they need to do in order to then be excited, in order to make use of the energy in the electric field you've applied. An electric field itself can't do that, but you could do it optically. You could like optically send in electromagnetic radiation, and if the photon energy is large enough, it can get them to jump across. We call those materials light-dependent resistors. Now, for an insulator, I suppose you could do it optically as well. That's true. But the big difference between them is thermally. If you make the material hotter and hotter and hotter, that can provide the 3/2 kT, average kinetic energy is 3/2 kT, or if you're in the IB, kBT. That formula shows you that as the temperature rises, the kinetic energy of the atoms is rising, and that can transfer to the electrons, and electrons can be pumped up across the energy gap. The phrase that people doing research on this use is promoted up. And for a semiconductor, you can get electrons jumping across the energy gap because of thermal effects, like you just warm up the material. That creates the thermistor. For an insulator, the temperature that you would have to raise it to in order to get electrons to jump across the gap would be enough to basically destroy the material. Like you'd need to get it to about 10,000–12,000 degrees, and no solid is going to stay at a solid at that temperature. So it's just thermal promotion of electrons across the energy gap. It's just not an option for insulators because the gap's just too big. You could still optically excite them, just have to have quite high frequency, maybe quite dangerous. You might have to hit it with X-rays or something, which of course, you know, you have to be careful with because they can cause cancer. So what I'd like to do at the end of this session is I'd like to send you a small document that I produced, which basically discusses, not in the way that we've done it, but basically discusses this, and it asks a few questions like for you to consider. Like, for example, when we say that insulators don't have free electrons, but conductors do, why is that statement incorrect? So it gets you thinking about the stuff we've just talked about. And another one, what's the difference between a free electron and a conduction electron? Because conduction electrons are electrons that are taking part in the conduction process. And if you look at this, and remember, I said to you, the amount of energy that an electric field provides is like about a dot on this diagram there. So that's okay for an electron here, because one dot above it is fine. It can do that because there's an energy level there. They're so close together because there's ridiculous numbers of them that's an option. But for the semiconductor or the insulator here, that's just simply not an option. But what about an electron here? An electron down here? An electron down here, for the electrical properties, if it's going to conduct, it has to move up a tiny amount, but that's already filled. This lot is filled. An electron, my E didn't look very good there. Let me just make my pen slightly smaller. If I zoom in here and look at an electron there, that electron can also not take part in the conduction process, because the energy provided by the electric field, when you apply like a voltage, is only a tiny amount, and that's filled. All this lot is filled. That lot's got electrons in it. Those energy levels there, the original energy levels, now they're part of a band. All those energy levels there, they're all filled. None of these electrons can take place in the conduction process. They're all free electrons because they're in a hybridized band. Free electrons are electrons that are in hybridized levels or hybridized bands, energy bands. But the only ones that can conduct are the ones sitting at the top. They're the only ones that can conduct, because only they are sufficiently close in energy to unfilled levels and can therefore make use of the energy in the okay, I don't know what I'm doing now. Yeah, that's it. In the energy of the field. So I'll let you have a look at that and have a read of it. It's about 4 pages. It goes through this lot. Just have a read of it and see if it makes sense with the notes that we've made. Now, how does this link to the concept of degeneracy? Okay, next week, in the next session, we'll merge those two things together, and we'll use the concept of degeneracy and the fact that this is for the free electrons. This is a situation where I can use the degeneracy is directly proportional to e to the half. I can use that relationship because they are free when they are within the metal itself. I can't use it for the core electrons, but I can use it for the electrons in the hybridized levels. So you now have knowledge way beyond A level and IB. The knowledge that you have now is a better understanding of what causes conduction and what electrons, when we give you these sentences like, you know, like glass or wood or ceramic, they're insulators because they don't have free electrons. That's not true. Every solid has free electrons. The difference now is, it's not whether there are free electrons, it's whether there are conduction electrons, ones that can conduct. And the answer to that is, that depends on whether it's in a filled or a half-filled band. And more than that, it also depends on the energy of the electrons right at the top, at that little top. So it isn't just if the electrons are in a half-filled, they conduct. It's not that simple. It's a tiny number. It is fair to say electrons in a filled band cannot conduct electricity. That's correct. It is not fair to say electrons in a half-filled band can, because not all of them can. In this lot down here, The ones at the bottom here can't. It's better and more correct to say only a relatively small number of the electrons in a half-filled band take part in conduction. That's a more accurate statement.